So what you should be seeing on your screen right now is your page 5 in your notes. All right, it's kind of cut off, but hopefully you see everything. Okay, so 5 different types of reactions. The first one is synthesis, and so what I'm going to do right now is I'm going to walk you through what each reaction is. I'm going to give you just a very general look at it, and then we're going to spend a couple of days on each of them looking at specifically what they look like. Alright, so the first thing that I'm going to do is I'm going to show you guys synthesis reactions. So what you have in synthesis reactions is you have 2 reactants, and you always have 2 reactants. The first reactant is A, alright, and it's going to be one element plus another just element. So it's 2 elements as your reactants, and they're going to produce, and when I say produce, that means I'm going to draw an arrow. They're going to produce a compound. So that's going to be A, B. That is my compound. So they're going to combine together, they're synthesizing something, they're creating AB. Alright, so I'm going to show you what this means with a quick drawing. So in my first box, I'm going to draw my atom A. So this is my first element, and it's all by itself. And then atom B, which is all by itself. Okay, now their elements. Remember, if we're talking about an element, it could be a diatomic element, so keep that in mind, and I'll show that to you really quickly in the example I have for you. But right now, let's just look at them as single atoms. Okay? So what they produce is a compound, and they're going to be obviously chemically combined. So there is my B, and hopefully I get the same color. If not, bear with me. Here's my A. So they've formed a compound. Alright, so that's a simple synthesis reaction. Now, a good example, if I take magnesium, and we'll be doing an example like this in the lab, if I take magnesium as a solid, alright, which is an element, and I add oxygen to it, O2, remember, yeah, sure, there are 2 oxygens bound to each other, but since they're the same type of atom, it's still considered an element. So here you've got 2 elements, just like here, 1, 2. Alright? When they react together, they're going to form a compound. So you're going to have Mg and O bound to each other. Alright? As soon as you create compounds in your head, you should be crossing your charges. Alright? Because you're going to have Mg and O together. Mg has a +2 charge. O has a -2 charge. So what you'll get is just MgO. Now, if you're uncomfortable writing that because you're not comfortable crossing your charges, you need to go back and review that. Alright? But this is one example of a synthesis reaction. Now, if you notice it's not balanced yet, I have 2 oxygens on this side, 1 on this side. So I need to put a 2 right here. Now, I've messed my magnesiums up because I have 2 magnesiums, so I'm going to put a 2 right there for my magnesiums. Alright? That's synthesis. 2 separate elements combined to form a compound. Now, decomposition is the exact opposite. You have 1 compound, alright, and when they react, and we'll look at what makes it react, it's going to break apart. It's going to decompose into A and B. Pretty simple. Okay? So, for example, if you have a compound that looks like this, okay, and actually, guys, I'm sorry, my arrows here are drawn incorrectly. I'm hoping on your notes they're drawn correctly. This should be an arrow right here, okay, and this should be the plus sign. Okay. Then what's going to happen is they're going to split apart into their separate atoms. So here's your, I believe that was A, all by itself now, not part of the compound, and B is going to be all by itself now. And you're done. Okay, so it's the exact opposite of synthesis. Now let's look at an example. Okay, I give you mercury oxide, so I say, okay, I've got HgO. And it reacts. Now, since I'm given 1 compound all by itself, I automatically know it's going to be decomposition. Unlike here where if you have 2 elements that form 1 compound, you know it's synthesis. Here, if you have 1 compound, and it breaks apart, you know it's decomposition. So you get Hg as one of your products, and your other product is going to be O. Now remember, O can't exist by itself, so you need a 2. That's where your diatomic elements come in. Here's the tricky part. I'm almost done, but I'm not balanced. Okay? I've got 2 oxygens here. I've only got 1 on my reactant side, so I need to put a 2 right here. That makes my oxygens perfect. However, my mercuries, I only have 2 mercuries, therefore I need to put a 2 right there for mercury. Now I'm done. So notice synthesis and decomposition are the exact opposites. All right, single replacement is pretty cool. All right, if you see that you have one element all by itself and a compound, so an element plus a compound are going to react, what happens, okay, A is going to go in there and kick B out. Okay, so what you end up getting, A is now going to be bound to C, and B is going to be all by itself. So A literally went in, kicked B out. If you can imagine them like I guess B and C like dance partners. A is going to kick B out. A and C are now dance partners. B is all by itself and is lonely. All right. So if I'm going to draw this, here's A, all by his or her lonesome. Okay. And then here's B, bound to C. Now, once they react, A and C are now going to be bound together. So here's C, and instead of being bound to B, it's now going to be bound to A, and B is going to be all sad and all by itself. Okay, so that's single replacement. Now, an example I can give you, if you have zinc, I'm going to write over here for you to see. If you have zinc plus copper nitrate, so copper CuNO3 2. All right? What's going to happen when they react, zinc's going to come in and kick copper out. So copper is going to be all by itself. So it's going to kick copper out, and it's now going to form a bond with nitrate. So copper's all by itself, zinc has gone in. It's now dance partners with nitrate. So you're going to have the other product being zinc, ZnNO3 2. Now, the main thing I'm concerned about with all of these guys is you recognizing what the reaction is. Once we get into the the details of this, then I'll be getting into what the products will be and everything, and you'll learn how to do this. But most important, when you see this, when you see, oh, I have one element and a compound, and one element was kicked out and it formed a new compound, you automatically know it's going to be single replacement. All right? Double replacement is a little bit more tricky. Not really, though. They're literally just going to be switching partners. Okay? So A and D are now going to become partners. So I'm going to draw a line between these two. So rather than A being partners with B, A and D are now going to be partners, and B and C are going to be partners. So the way that I would write this would be A, D plus B, C. All right? So I'll draw this again. Here's my A. And just to save time, I'm going to draw it on this side. Okay. Here's B. Now it's not going to be bound to A and the product side. It's going to be bound to C. Okay. Here's C. And C is going to be bound to B. So notice they're just switching partners. It's kind of like a whole little dance that they're doing. More complicated than with single replacement, but still very doable. All right. So if you notice, everyone just switched partners. Okay. So let me give you an example of when this would happen. Let's say I have calcium bromide. So CaBr2. All right. And I'm going to add to that silver Ag nitrate O3. Okay, so if you notice, Unlike single replacement where you have one element and a compound, here you have a compound and a compound. So what you should be noticing, synthesis, you start off with element, element. Here you've just got one compound for decomposition. Single replacement, you've got an element and a compound. Here you've got a compound and a compound. Okay, so now they're just going to switch partners. So Ca, instead of being partners with Br, is going to be partners with NO3. Okay, so it's going to be Ca, and we'll go over crossing charges again, I promise. That needs a 2 right now. Plus, now Ag is going to be partners with Br. Okay, because C becomes partners with B. So it's going to be Ag, Br. All right, and if I look at this, this becomes kind of a balancing nightmare, but if you notice, I have 2 BRs here and only 1 here, so I need to put a 2 right here. Now I have 2 AGs, so I need to put a 2 right there. All right, and now I'm done. Okay, so single and double look a little bit more complicated. You get more of your having to cross your charges. We'll work on it, I promise. But you will have to review that very soon. Okay. Last reaction, I'm almost done, I promise. I think is the easiest. It's combustion. Okay. The boom booms that I promised you in the beginning of the year are finally here. What you do in combustion, you take a hydrocarbon, which is just hydrogen and carbon, okay, and you add oxygen gas. All right. And what you get for a product every single time, no matter what you add, you will always get CO2 and H2O. All right, so if we look at this, let's first look, I'll give you an example of C6, H6. Okay, so you're going to just add oxygen gas. Remember, oxygen doesn't exist by itself, so you have to add O2. All right. And it's going to yield every time, no matter what, CO2 plus H2O. All right? I'm going to turn a different color. The most challenging part about combustion, guys, and I'm actually going to leave this part blank. If you want to draw in this, you can. I think it's going to be a pain in the butt with the C6, so I'm going to leave this part blank. But the biggest pain in the butt for this is balancing. So in order to balance combustion reactions, okay, I always think of CHO. I get back to my nerdy days of Cho Chang with Harry Potter. Think of fire coming out of her wand. You first want to balance your carbons, then your hydrogens, and then your oxygens. Okay, so here I have 6 carbons, so I need to put a 6 out front here to make this 6 carbons as well. Then I need to take care of my H's. Well, here I've got 6, here I've got 2, so to make this equal to 6, I need to put a 3 out front. Notice when I count this up, 6 times 2 is 12, 3 times 1 is 3, so I've got 15 oxygens here. To make this 15, I need to make this 7.5. Okay, which is fine to do at first, but then you need to change it. And remember, you can multiply everything by 2 to get rid of that half because you can't have a decimal. So this is going to be 2, this is going to be 15, and this is going to be 12, and this is going to be 6. Okay, so the hardest part of combustion is just balancing. All right, so if we review really quickly, last part, synthesis, you've got two single elements to form one compound, all right, and those single elements could be diatomic elements, so look out. Decomposition, you've got a single compound. For single replacement, you've got a single element plus a compound, okay. Double replacement, 2 different compounds. In combustion, you've got a hydrocarbon, meaning anything with just carbon and hydrogen and oxygen, producing CO2 and H2O. All right, I hope this helped you guys, and check online for any additional homework that I assign.